In this video, we will be talking about derivatives of logarithmic functions and inverse trig functions. The logarithmic function with base b is denoted y equals log base b of x, where b is positive and not equal to 1, and x is a positive real number. Remember that the domain would be 0 to infinity. We can only take the logarithm of a positive number. And also remember, we have logarithmic form here, and we can switch to exponential form. So that is y equals log base b of x if and only if b to the power of y is equal to x. Now, a mnemonic device one of my former students taught me a long time ago is to rely on bay. And if you have it written in this form, bay is base, argument, and then e is exponent. So example 1 says find x. We'd like to take log base 3 of 81. So if I can rewrite this in exponential form using this acronym bay, that gives me that 3 to the power of x is equal to 81. And the value of x that makes this statement true is x equals 4 because 3 to the 4th power is equal to 81. In part B, we have log base 25 of x is equal to 1/2. And again, we can rely on bay. So BAE, if I'm rewriting this in exponential form, I have 25 to the 1/2 power is equal to x. And remember, that is the same thing as the square root of 25. And so the square root of 25 is 5. So here we have x is equal to 5. Part C, we have log base x of 1 over 100 is equal to -2. So again, if I use bay, I have my base is x, my exponent is -2, and then my argument is 1 over 100. And the left-hand side, x to the -2, I can rewrite that as 1 over x squared is equal to 1 over 100. From here, I can cross multiply. If I cross multiply, that gives me the new equation x squared equals 100. And then if I take the square root of both sides, normally we would get x equals plus or minus 10. However, remember that when you're talking about a logarithm, the base of a logarithm must be a positive number. So we get that x is equal to 10 in part C. So here are a bunch of properties of logarithms, and then below that we have laws of logarithms. Sometimes you will hear these called the product rule for logarithms. Sometimes you will hear this one called the quotient rule for logarithms. And the last one you might sometimes hear it called the power rule for logarithms. Not to be confused with the product rule, quotient rule, and power rule for derivatives, so don't get those confused. And then finally, we have the change of base formula, which comes in handy sometimes, especially when you have a calculator that does not have all of the log bases. Sometimes if you're dealing with a scientific calculator or a simpler calculator, it'll only have the natural log and the common log, so the change of base formula comes in handy. Example 2 says evaluate each expression without a calculator. In part A, what I can do is I can utilize the product rule for logs, and I can combine this into a single logarithm, and that would be log base 6 of 18 times 12. And 18 times 12 is 216. And then this is essentially asking, suppose this was equal to question mark. If I used bay, then that would say 6 to what power is equal to 216, and the value that makes this true is 3. 6 to the 3rd power is equal to 216. So this expression is equal to 3, and that's our final answer for part A. All right, for part B, I can use the quotient rule for logarithms, and I can rewrite that as log base 2 of, because they're being subtracted, I can condense that into a logarithm of a quotient. So we have log base 2 of 80 divided by 5. which is equal to log base 2 of 16. And then we are asking ourselves, what power of 2 gives us 16? And that is equal to 4. All right, in part C, we have negative 3 times log base 5 of 1/5. There are a few different ways we could go about doing this. I'm going to rewrite 1/5 as 5 to the negative 1 power, and then depending on which logarithm law or property you'd like to use, one way you could do this is using the power rule, or if you scroll back up or rewind, you saw that one of the properties says that log base b of b to the x power is equal to x, and so this here is equal to negative 1, and then we have negative 3 times negative 1, so that ends up being positive 3. Now that we got some review and practice on just the basics of logarithms, let's start doing some calculus. Example 3 says differentiate the following functions using implicit differentiation. So part A, we have y equals the natural log of x. And in the previous video, when we talked about implicit differentiation, that is when we are taking the derivative of something that's in implicit form. Now you might be looking at part A and you say y equals natural log of x is in explicit form, and so how would we use implicit differentiation on this? Well, I don't know what the derivative of the natural log of x is. If you look and preview down here in our table, it tells you that the derivative of the natural log of x is equal to 1 over x, but I actually want to derive that formula and see where that comes from. So what I'm doing is I'm actually going to rewrite this in exponential form, and in order to use Bay on this, remember that the natural log is really like us writing log base e of x is equal to y. That's not typically how we write it. We write it like natural log of x is equal to y, but that's what it means. It means that the base is e. So if I'm relying on Bay, this would be my base, my argument, and my exponent. And so I can change this into exponential form, and that would be e to the power of y is equal to x. Now what I can do is I can go ahead and use implicit differentiation by taking the derivative with respect to x of both sides of this new equation that we have. So I have the derivative with respect to x of x on the right-hand side, and the right-hand side is going to be easier to calculate. The derivative of x with respect to x is 1. And then on the left-hand side, I will use chain rule. And the derivative of e to the power of y with respect to y is e to the power of y. So I'm going to come over here. We have e to the power of y times dy dx is equal to 1, and then my goal is to isolate dy dx. So I get dy dx is equal to 1 over e to the power of y. Now you might be asking yourself, wait, I thought you just said that the derivative of the natural log of x is 1 over x. Those are not the same thing, but actually, even though it doesn't look like they're the same thing, they are, because if you remember from earlier, we know from Bay that x is the same thing as e to the y based on our original definition of the function. So I can make a substitution and say dy dx is equal to 1 over x. And this is our final answer. So you have helped me to derive the formula for the derivative of the natural log of x, which happens to be 1 over x. Let's do something very similar for part B. We have y equals log base b of x. I'm going to convert this into exponential form. If we do that, we end up getting b to the power of y is equal to x. And I forgot to write here, remember that y prime and dy dx mean the same thing. So from earlier, we found that that was equal to 1 over x. Okay, so going back to part B, I'd like to now use implicit differentiation. So I'm going to take the derivative with respect to x of both sides. Once again, the right-hand side is going to equal 1, And then on the left-hand side, I am going to take the derivative with respect to y of b to the power of y and multiply that by dy dx. And remember, the derivative of b to the power of y is going to equal b to the power of y times the natural log of b, and then we still have dy dx is equal to 1. From here, if I isolate dy dx, we get dy dx is equal to 1 over b to the power of y times the natural log of b. But remember, just like from before, we have this from our original definition. We know that b to the power of y is equal to x, so we can make that substitution in and say that dy dx is equal to 1 over x times the natural log of b. And oh look, that matches this formula that we have down here, so this completes part B. Now that we have those formulas derived for the derivatives of the natural log function and the regular log function, example 4 says find the following derivatives. We can use those formulas that we just came up with. So for part A, we're trying to find the derivative with respect to x of the natural log of sine squared x. So I do just want to emphasize that we're now using chain rule. So a more general formula is that if I have the derivative of the natural log of something, and in a lot of formulas or textbooks and things like that, instead of something, it'll say something like u, where u is some function of x. So the natural log of u is equal to 1 over u times u prime. So in this case, our u is sine squared x. So we're essentially using chain rule here. So the derivative of the natural log of something is equal to 1 over whatever the something is. In this case, it's sine squared x times the derivative of that something. So sine squared x, in order to take the derivative of that, I'm going to use power rule. And my new power on sine would be the first power. And then I have to use chain rule again by multiplying by the derivative of the inner function, which in this case is sine. So that would be multiplied by cosine. So let's clean this up. My numerator will be 2 sine of x, cosine of x, and my denominator is going to be sine squared x. And notice that we have multiplication in the numerator, and then we have 2 signs in the denominator that are being multiplied. So we can simplify this to be 2 times cosine of x, and over 1 of the sine of x remains. And then if we use trig identities, cosine divided by sine is cotangent, so we could write this as 2 times cotangent of x. For part B, we're taking the derivative with respect to r of r squared times the natural log of 2r plus 1. In order to figure out what this is, we're going to need to use product rule. So we have the first function times the derivative of the second function. Because it's a natural log, I'm going to do 1 over the something, which in this case is 2r plus 1. And then I need to multiply by the derivative of the something. The derivative of 2r plus 1 is 2. And then plus the second function times the derivative of the first function, which in this case would be 2r. If we clean this up, then my first fraction here will be 2r squared over 2r plus 1 plus 2r times the natural log of 2r plus 1. And there's our final answer for part B. Sometimes we will encounter functions that we want to take the derivative of that will require something called logarithmic differentiation. One instance to use this is when we have a function that is made up of a function in the base and in the exponent. The first step in logarithmic differentiation is taking the natural logarithm of both sides of the equation. All right, so example 5 says dy dx, or find dy dx for the given functions. Part A says y equals x to the power of x. Now, why can't we just use the power rule on this? Well, the power rule, in order for us to take the derivative of something like x to the nth power, n has to be a constant, and then we have n times x to the n minus 1. Here, our exponent is x, which is not a constant, so we cannot use the power rule on it. Please be careful and don't use the power rule on this. We have to use logarithmic differentiation, and we want to take the natural log of both sides as our first step. So let's start off in part A by taking the natural log of both sides. And the whole reason that we want to take the natural log of both sides is because we can use the power rule for logarithms. And now I have the natural log of y is equal to, if I bring my power out and multiply it on the outside, we have on the right-hand side x times the natural log of x. Now what I can do is I can use implicit differentiation on both sides by by taking the derivative with respect to x on both sides of our equation. Now, on the left-hand side, I need to switch this up into the derivative with respect to y of the natural log of y times dy dx. And then on the right-hand side, thankfully, this is all a function of x, and so I just need to use product rule here. So we have the first function times the derivative of the second function plus the second function times the derivative of the first function. Okay, so now what I want to do is I want to take the derivative of the natural log of y with respect to y, and that's going to end up being 1 over y. I don't want to forget the dy dx, so we're multiplying this by dy dx is equal to x times 1 over x is 1, and then plus the natural log of x. Now what I'm going to do is I'm going to multiply both sides of my equation by y, because I'm trying to isolate dy dx. Doing so will give us dy dx is equal to y times 1 plus the natural log of x. Now, one thing that we want to be careful about is that if you look at our original function, we have y equals x to the power of x. This is in explicit form. And so we want to try to see if we can get our final answer in explicit form. And because we know that here y equals x to the power of x, I can actually make that substitution right here for y. And if we do that, we get dy dx is equal to x to the power of x times the quantity 1 plus the natural log of x. And here we have our final answer for part A. All right, moving on to part B. Once again, I need to use logarithmic differentiation because both the base and the exponent are functions, and I cannot use the regular power rule for derivatives on that. So let's start off by taking the natural log of both sides, and on the right-hand side, I'm going to be able to use the power rule for logarithms, and so if I rewrite this, I have the natural log of y is equal to cosine of x times the natural log of x, and from here, I can use implicit differentiation and take the derivative of both sides with respect to x. On the right-hand side, I will need to use the product rule, and on the left-hand side, I'm going to need to use the chain rule. So on the right-hand side, we have the first function times the derivative of the second function plus the second function times the derivative of the first function. And then that's going to be 1 over y times dy dx equals cosine of x over x plus, I guess because we have that negative, I'm going to change this to minus times the natural log of x. From here, I would like to isolate dy dx, so I'm going to multiply both sides by y. Doing so gives us dy dx is equal to y times cosine of x over x minus sine of x times the natural log of x. Now again, because of our original definition of our function, I can substitute in y equals x to the power of cosine of x for this y here. So finally we get that dy dx is equal to x to the power of cosine of x times the quantity cosine of x over x minus sine of x times the natural log of x. And that's our answer for part B. All right, so looking at part C, we actually don't have to use logarithmic differentiation on this because I can rewrite this as x minus 1 over x to the 4th plus 1 to the 1/2 power, and I would need to use power rule, and then to take the derivative of the inside, I would use the quotient rule, and so I'd use power rule, chain rule, quotient rule, and that just seems kind of like a lot. So even though we don't have to use logarithmic differentiation in part C, it's going to help us out, and let's see how that works. So if I take the natural log of both sides, then I can use the power rule for logarithms and rewrite this as 1/2 times the natural log of x minus 1 over x to the 4th plus 1. And I can also use the quotient rule for logarithms to rewrite the right-hand side as 1/2 times the natural log of x minus 1 minus the natural log of x to the 4th plus 1. And from here, let's take the derivative of both sides with respect to x. So I'm now taking the derivative, and we're using implicit differentiation. So the 1/2 is a constant here, so I can pull this outside of my derivative and just take the derivative of the inside of my brackets and then multiply by 1/2. And on the left-hand side, I will take the derivative with respect to y. And I need to use chain rule, so I will multiply by dy dx equals 1/2. I'm going to take the derivative with respect to x of the natural log of x minus 1 minus the derivative with respect to x of the natural log of x to the 4th plus 1. And here we have 1 over y times dy dx is equal to 1/2 times the derivative of the natural log of something is 1 over something times the derivative of something, but the derivative of x minus 1 is 1, minus 1 over something times the derivative of something, which in this case would be 4x cubed. All right, so let's multiply both sides by y to isolate dy dx. So we have dy dx equals 1/2 y times 1 over x minus 1 minus 4x cubed over x to the 4th plus 1, like that. And the last thing I just want to do is I want to substitute y for the square root of that fraction. And so we have 1/2 times the square root of x minus 1 over x to the 4th plus 1 times 1 over x minus 1 minus 4x cubed over x to the 4th plus 1. And this very messy thing here is our final answer for dy dx. Now, if you're feeling super adventurous, you can try to take the derivative the other way that we originally mentioned with the power rule, chain rule, and quotient rule, and you should get the same answer. However, it's probably going to take some work to algebraically see that the derivative that way and the derivative that the way that we solved it would come out to be the same thing, and it's going to probably require some algebraic manipulation. I will leave that up to you if you would like to do that. All right, so example 6, we want to find the derivative dy dx if y equals arctangent of x. And once again, I don't know what the derivative of arctangent of x is, and so we're going to need to use implicit differentiation. But how are we going to do that? Well, it works very similarly to what we were doing before, and we're going to take tangent of both sides of this equation. Doing so will give me tangent of y is equal to tangent of arctangent of x. And this is very similar to what we were doing with the logarithms. And just a quick review if you don't remember from pre-calculus, when you're learning about functions, you learn that if you have a function and its inverse, if you compose them, they end up equaling x like this. So, and usually composition is not commutative, but in this case it is if your two functions are inverse functions. And so why am I saying that? Well, tangent and arctangent are inverse functions of each other. And remember arctangent, another way that we could write that is tangent inverse of x. That is not an exponent. It is just the notation for inverse trig. So now at this stage, we have tangent of y is equal to x. And from here, we can use implicit differentiation. Let me clean up the screen a bit. All right, so at this stage, I would like to take the derivative with respect to x of both sides of my equation. And on the left-hand side, we will need to use chain rule and make this the derivative with respect to y of tangent of y times dy dx, and this is equal to the derivative of x with respect to x is 1. Now we want to take the derivative of tangent, so that will give us secant squared y times dy dx is equal to 1. If I isolate dy dx, then we get dy dx is equal to 1 over secant squared y, and using trigonometric identities, and more specifically the reciprocal identity, this is the same thing as cosine squared y. Now, just like before, we actually can get this into explicit form. It's just going to need to, it's going to require a little bit more work of us. So let's see what that's going to do. We originally said that if we have y equals arctangent of x, if we take the tangent of both sides, we ended up with tangent of y is equal to x. And when you take trigonometry, you learn about this mnemonic device called SOHCAHTOA. And SOHCAHTOA tells us that when you have tangent, that is equal to the opposite over the adjacent side length in a right triangle. So if I draw some arbitrary right triangle, and let's say that this angle here is y, if we know that tangent of y is equal to x, which x is the same thing as x over 1, that means that we have the opposite side length over the adjacent side length is equal to x over 1. So in this picture, we could say that our opposite side length to our angle y is x, and that this is 1. And if I want to know the length of the hypotenuse, maybe I'll just call that question mark for now. If I want to solve for that, I would use the Pythagorean theorem, which would say x squared plus 1 squared is equal to question mark squared. And then if I solve for question mark, I would get the square root of x squared plus 1. So let me just erase the question mark here and fill in the length of my hypotenuse to be the square root of x squared plus 1. Why was Or why are we doing all this work to fill in the information on this right triangle? Well, we have here that the derivative dy dx is equal to cosine squared y, and from our picture, we should be able to figure out what cosine of y is equal to. Remember that this is the same thing as the cosine of y quantity squared. So if I wanted to figure out cosine of y in our picture, we can go back to SOHCAHTOA. It tells us that cosine is equal to the adjacent side length divided by the hypotenuse. So in this case, we can see here that cosine of y is equal to 1 divided by the length of the hypotenuse, which is this. So let's fill that in down here. Cosine of y is equal to 1 over the square root of x squared plus 1. And what I'm doing is I'm squaring that quantity. And when I square a fraction, I can square the numerator, which is 1, and I can square the denominator, which would get rid of the square root in this case, and we end up with this. So let me just re-emphasize, if we have y is equal to arctangent of x or tangent inverse of x, we end up with its derivative being 1 over x squared plus 1. And this is our final answer for example 6. Oh, look at that. Here in this purple box, we have the derivatives of all 6 inverse trigonometric functions. And remember that we just got done taking the derivative of arctangent, and we derived this formula for 1 over 1 plus x squared, or the same, that we got 1 over x squared plus 1, but addition is commutative, so that's the same thing. We can derive the formulas below in a similar way that we derived the formula for the derivative of tangent inverse in the previous example. You do need to memorize these formulas. They are important, and they are going to show up again in Calculus 2. So example 7 says differentiate the following functions. I have in part A, I'm trying to find y prime, and before I find y prime, why don't I factor out the constant of 1/5? So that leaves me with 2 to the power of x times sine inverse of x. And so I'm going to use product rule. I have my first function times. Now, a mnemonic device or a trick that I always tell my students is whenever you're taking the derivative of a trig function or an inverse trig function, and that function starts with a c, that means that the derivative is going to end up being or having a negative sign in the front. Now, if your trig function or inverse trig function does not have a c or start with a c, then its derivative will not have a negative sign in the front. So we are taking the derivative now of sine inverse, so that's going to be 1 over the square root of 1 minus x squared, and that's just from me looking up at the picture. But again, we do need to memorize these formulas. So for now, you can just kind of look up at the table, but do have those memorized. Plus, the second function times the derivative of the first, and we just got done talking about this earlier because we were deriving the formula for the derivative of a logarithmic function. So the derivative of 2 to the power of x is 2 to the power of x times the natural log of 2. All right, so I just went ahead and simplified my answer a little bit. So here is my final answer for part A. Let's move on to part B. We are trying to find q prime of y, and again, we're taking the derivative of cosine inverse, and cosine starts with a c, so that means that its derivative will involve a negative sign in the front. So I have negative 1 over the square root of 1 minus whatever the inner function is, squared. So in this case, it'd be e to the power of y quantity squared. And then I need to use chain rule and multiply by the derivative of the inner function, which in this case would be e to the power of y. And if I just clean this up, we have negative e to the power of y over the square root of 1 minus. And if I square e to the y, that gives me e to the 2y. So here is my final answer for part B. And that concludes this video. Thanks so much for watching.